Hello! In this video I'll run through an example of Euclid's algorithm. Which is designed to compute first of all the greatest common divisor of a pair of numbers, and then it can be turned upside down and used for expressing this greatest common divisor as a combination of two numbers. So I will illustrate both runs of this algorithm on a concrete pair of numbers. Let's start with something like 1, 2, 3, 5, 6, 7. So these are the numbers. First of all, we have to compute the greatest common divisor of, and then write it as a combination of these two. And it will be using the property of the greatest common divisor that if you have a pair of numbers, the GCD, the greatest common divisor, is the same as a pair of these numbers. And we can assume that A is not smaller than B, so that both numbers are natural numbers. But even if it's a negative, if it's an integer, still it makes sense. The greatest common divisor still be meaningful, still be the same for the pair in here and in here. And using this property, we will be doing it in steps, so we'll be decreasing the larger by the smaller, really iterating this subtraction as many times as necessary to make the difference less than B. So we can subtract B from A as many times as it takes to get the remainder, to get the difference less than B. And that is the Euclid's division. So we will be doing Euclid's division in steps, and we will be recording it for the future use. For the sake of computing the greatest common divisor, it's not really so necessary, but for the going upside down, for the finding the expression of the greatest common divisor as a combination of two numbers, it is necessary. So let's start with this first run of Euclid's division and take the larger and write it as the smaller, and that was done in the previous video. So 4 is Q in this case, and the remainder is 75. So that allows us to replace 5, 6, 7 by 75, and the statement in this equation is that the greatest common divisor of this pair is the same as of this pair. Then we can turn 1, 2, 3 into some number of copies of 75, and it's just one number of copies, and then the remainder will be 1, 2, 3 without 75, so that will be 23 and 25 together, giving us 48. And that computation allows us to replace 1, 2, 3 with 48, and then 75 is the same as before. So this round we will be dividing 75 by 48. Again, it's one whole piece of 48, and then the remainder is the difference, which is in this case 27. And that we can replace 75 by its remainder, which is 27. The next is to divide 48 by 27, so one copy of 27 fits inside, and record the remainder, which is going to be 21. So that is what we put instead of 48. And the next is to take 27 and divide by 21, and the remainder is going to be 6. So that is what I can replace 27 by. And the almost done, 21 divided by 6, not once. I've got written it wrong here. It's 3 times we can squeeze 6 inside 21. So 18 is still less than 21, and taking out of 21 it will leave us with 3. So we're almost done, really one step away, because 6 is just 2 copies of 3. So when we do the division, the remainder will become 0, and so the GCD is just 3. But the first meaningful equation is in here. Well, first of all, the conclusion is that the GCD of the original number, the greatest common divisor of these two, is 3. So now the task is to write down the greatest common divisor as a combination of the numbers. So find U and V, which will make it true. So express 3 as a combination of these two numbers. We will be doing it bottom up. So first of all, we will say take it here and express 3 as a combination of 6 and 21. It's just taking this equation and slightly rewriting it. It's 21 once minus 6 3 times. That is the equation here, right? I'm seeing my greatest common divisor, and then I'm seeing the numbers of which it is the greatest common divisor, 21 and 6. But here I need to get up to here. I need to write 3 as a combination of these two. So I will be doing it in steps, promoting this expression to the expression in terms of 21 and 27 and so on. So the first step is to, sorry, what did I do? 6, yeah. The first step is to look at the smallest and look at how it is itself a combination of 27 and 21. And the concrete expression here again is 6 is equal to 27 ones minus 21 ones. So I will substitute it in here, and then I will collect the terms and write the answer. So the this will be the answer for 3 as a combination of 21 and 27. So just by substituting, I will have 21 ones and then negative 3 copies of 6, and each copy of 6 is 27 minus 21. I have 3 of them, so when I collect the terms, I have 21 once, and then I have 21 3 times. Negative negative gives me positive, so I'll have 21 4 times in total, and then negative 3 copies of 27. And that is the answer for the expression of the GCD of 21 and 27 as a combination. But I still have some steps to do. So now I have to replace 21 by 27 and 48. 21 is 48 minus 27. So that I can substitute in here. 21 4 copies first, and then 20 instead. Sorry. Yeah. It's 21 which I'm replacing, so I'll just cross it out. So 21 is this 48 minus 27, and I have 4 copies, and then 27 3 copies. So that I have to just bend it around. I have to collect the terms on this line, so that will be 48 4 copies, and then 27 negative 3 copies and negative 4 copies. So 27 will come with coefficient 7, negative 7 to be precise. So that is the answer for the expression of GCD on this level. 3 is still equal to this combination. It's not what I need yet, so I need to get rid of 27 at the expense of 75 and 48. So that's what I will substitute in here. So I'll have 48 first 4 copies, and then 75 minus 48 7 copies. So that collected will give me a negative and negative positive 7 copies of 48 on top of 4. So that will be in total 11 copies of 48, and then 75 comes with multiple negative 7. Next round is to get rid of 48. 48 from this equation is 1, 2, 3 without 75. So that's what I can plug in here. That will give me, so just make a separation, that will give me 1, 2, 3 minus 75 times 11, but then I have negative 7 copies of 75. So that organized better give me 1, 2, 3, 11 times, and then negative 11 and negative 7 in total give me negative 18 copies of 75. So that is one step away now from my final answer. We can get it by taking 75 and expressing it as a difference of these two terms. So don't have much space left, but I'll write it here. 75 is equal to 567 without 4 copies of 1, 2, 3. So that's what I can plug in here. 1, 2, 3, 11 copies without 5, 6, 7 minus 1, 2, 3, 4 copies, all 18 times. And that is the last computation I need to make. So how many copies of 123 I have? 11, and then negative 4 times 18. The 4 times 18 is 40 plus 4 times 8, which is 32, and so I have 72 on top, so on top of 11, so that will give me 83. So 1, 2, 3 comes with coefficient 83, and then with minus I have 5, 6, 7, just 11 times. So that is the final answer. The greatest common divisor, oops, no bracket here, just comma, 5, 6, 7 of 1, 2, 3 and 5, 6, 7 is as a combination of these two numbers. Well, first of all, it is equal to 3, but then as a combination of these two numbers is 1, 2, 3, 88 times, sorry, 83 times. And with negative 5, 6, 7, 18 times. And that you can verify now, because it's just simple arithmetic, maybe with the help of calculator, to take this product, and the difference will be 3. So that is the that is our example of Euclid's algorithm applied to two problems. First, finding the greatest common divisor, that was this chain of calculations, and then using them in reverse to find this expression of the greatest common divisor as the combination. Well, that's it for this video. See you later.